Alrighty, section 4.2. In the last section we talked about Dalton's atomic theory, and much of Dalton's atomic theory is still accepted today. So a couple of things we want to talk about. Atoms are now known to be divisible. They can be broken down into smaller particles called subatomic particles, which we'll talk about today. And we also understand about nuclear fission, where we can break atoms apart through a nuclear reaction. And the other part is that we talk about isotopes. So not all atoms are exactly the same mass, but we'll talk about that a little more in the next section. And you should be aware that the three kinds of particles that we'll talk about in an atom are electrons, protons, and neutrons. And in this section, we're going to be talking about how scientists actually discovered these three subatomic particles. The first scientist we're going to talk about is J.J. Thomson, who is credited with discovering the electron, and electrons we know now are negatively charged particles. So here's how he discovered the electron. Well, at this time period, we have to remember that electricity was all the rage, and there was lots of new electricity experiments going on. They were electrifying everything and performing all kinds of experiments with electricity. So he used electric current through a gas tube, and there were metal discs or electrodes at either end, and he passes electric current through this gas sealed up in these glass tubes. Well, what happened when you turned on the electricity is there was a glowing beam inside the tube, and they called these beams cathode rays, and they traveled from the cathode here, which was the negative, and they traveled in this direction to the positive disc they called the anode. So Thomson began experimenting with these cathode rays, and one thing he found was that if he had a positive and negative plate, that the ray was deflected by the metal plate. So it was repelled away from the negative plate and toward the positive plate. Thomson understood that opposites attract, so he concluded that cathode rays were negatively charged particles. He used the word corpuscles. Today we call them electrons. Cathode rays also are deflected by magnets, and as you can see here, the rays bending up, being attracted to the magnet. Thomson did further experiments with these cathode rays and worked to measure the ratio of the electron charge to mass. So he wasn't actually able to calculate the actual charge or mass, but he calculated the ratio. And he concluded that electrons, therefore, are the component of all atoms. Another scientist, Robert Millikan, was actually able to determine the quantity or the amount of charge on an electron. His experiment used oil droplets that he was able to suspend between two charged plates, and by changing the voltage of the plate, he was able to see how quickly the droplets fell, and that allowed him to determine the actual charge. By finding the charge of the electron and using Thomson's charge to mass ratio, he was able to calculate also the electron's mass. So Millikan is credited for finding the charge and the mass of an electron. And the values that he came up with are very similar to those our accepted values today. Today we know that an electron has 1 unit of negative charge, so an electron is a -1 charge, and its mass is 1/1840th the mass of a hydrogen atom. So it's very small compared to the rest of the mass of an atom. Now, electrons are not the only thing found inside an atom, and in 1886, a scientist named Goldstein observed a cathode ray tube, and he observed and found rays traveling in the opposite direction of the cathode rays. Well, for every negative, we have a positive. So he concluded from experiments that they were composed of positive particles, and today we call those protons. Quite some time later, in 1932, the neutron was discovered. James Chadwick confirmed the existence of the neutron. And they are subatomic particles with no charge. Neutrons are neutral, but the mass is almost the same as a proton. It took so long to discover the neutrons because they have no charge. This table summarizes the three subatomic particles. This symbol is how we will typically abbreviate the different particles. Their charges, electrons with a -1 charge, and protons with a +1 charge, and neutrons being neutral. The relative mass, understanding that the mass of a proton being assigned arbitrary value of 1, and neutrons have about the same mass, and that the electron rather, has a much smaller mass. The actual mass in grams is over here. I wouldn't expect you to really know that for certain. Understanding these three columns would be the most important. We also understand that even though protons and neutrons are very small, they are made of smaller particles yet that we call quarks. And there's different kinds of quarks even, and that's a whole nother subject and a whole nother course. Once scientists understood that we had these different particles, and then they began to question, what does it look like on the inside? And so many scientists, including J.J. Thomson, who remember discovered the electron, thought it was probably likely that electrons were evenly distributed throughout the atom. And this model is called the plum pudding model. Electrons were stuck into a lump of positive charge. This is what the plum pudding model looked like. So we had an atom here that was all made of positive charge, and interspersed then throughout were small negative electrons. So Ernest Rutherford was a New Zealand chemist, and actually was awarded the Nobel Prize for his work, so it was pretty important. So he actually set out to prove the plum pudding model was correct. So they devised an experiment called the gold foil experiment. So their idea was they used alpha particles, which actually have a +2 charge, so they're positively charged, and they're really a helium atom that lost the electron, so it's just the protons in the center. So in his experiment, he shot these alpha particles, seen here in the red, through a very thin sheet of gold foil. And what they expected to happen was that most of them would pass straight on through, no problems. Maybe a few of them would be just slightly deflected, because of the positive charge. Remember, it was supposed to be spread out throughout the whole of the gold atoms. And that is, in fact, what happened. Most of them went straight through or were slightly deflected. As you can see here, they went straight on through. Maybe a few of them were slightly deflected, but they were really surprised. And what happened was that a few of them actually were deflected back toward the source, or at a very large angle. And this was very surprising. They were not expecting this to happen at all. This led Rutherford to actually suggest a new model, and he proposed that the atom is mostly empty space, and this is why most of the alpha particles did not deflected or went like straight through. And then the reason that some of them bounced way off was that in the center of the atom was a very dense region of positive charge called the nucleus. This model is now known as the nuclear atom because it has a nucleus. So we know the protons or neutrons are together in the nucleus, And then the electrons are distributed around the nucleus and take up almost all of the volume or the space. According to this model, the nucleus is very teeny tiny and very densely packed compared to the rest of the atom. So if an atom was approximately the size of a football stadium, so we blow it up great big, the nucleus is only about the size of a marble sitting on the 50-yard line. So very small compared to the rest of the space. And we'll be talking more about the electrons and where they are at a later time.